Evet, herkese merhabalar tekrar. Saat 11.45. Buna göre programda bir sonraki etkinlik arka arkaya gelecek olan 2 tane konuşmadır. Çağrılı davetli konuşmalar olacaklar şimdi de. Eğer hazırsanız ilk konuşmacıyı ben davet edeceğim ve konuşmaya başlıyor olacağız. Okay, this is the second talk for today. We have another invited speaker here, and then the speaker, let me introduce her. Her name is Aybige Akıncı. Aybige Akıncı is a research associate in INGV in Italy. She had all the degrees in Turkey, in 9 Eylül University. And then since 2002, she's been a full member, associate member, research member in INGV. And then today, she's going to present a very interesting talk to you. And after the presentation, she's going to accept your questions if you have. I think we have some people just walking inside, so let me just start slowly, and then we will have her talk.
Hello, everyone. Thanks for coming. Before starting, I would like to thank everybody who organized this meeting and inviting me to give a seminar. I'm very pleased and honored to join you here, even in a virtual way. Today, I will talk about the seismic hazard assessments, current practices, and new challenges. In this talk, I will present you some results, mostly from Italy, as an outcome of several national and international projects I was personally involved in. Most of these projects had the objectives to develop and apply innovative approaches to improve the standards in the seismic hazard assessment and quantification. I would like to start by showing you a couple of slides on the essential information for the seismic hazard analysis. As we know, it can be defined as the probability that an earthquake will occur in a given geographic area within a given window of time and with ground motion intensity exceeding a given threshold. So the definition of seismic hazard already contains different elements and different parameters related to the space and time. It can be assessed both deterministically and probabilistically. However, the probabilistic method is most used and consolidated worldwide. After estimating the hazard, it's possible to evaluate the risk with building codes, designing for structures, planning for land use, determining the insurance rates. In this way, the seismic hazard analysis become the main topic and reference for different products. The mathematical definition of PSH is given by disintegration by Cornell in 1968. In this equation, we can easily distinguish that the hazard has two main components, which results from the rate of earthquake occurrence that can be obtained using earthquake rate forecast models, and the ground shaking, where we introduce the intensity measure relationship, where the ground motion parameters are presented as a function of distance, magnitude, and frequency. The annual rate of occurrence of earthquakes can be described with the Gutenberg-Richter relation for seismicity. But for this relation does not always correctly define the behavior of strong earthquakes on the fault structures. In this case, we consider the characteristic earthquake distribution, assuming that the total seismic moment for a fault source releases with a single maximum magnitude. Although in the traditional PSHA, The probability of occurrence is modeled as a Poisson process, where the predicted occurrence of future earthquakes is independent of the previous occurrence on the same source. This assumption is physically not valid for large events following the elastic rebound theory, and it can be defined by renewal models where the earthquake occurrence probability varies over time. The final product of this analysis is the hazard curve that presents the ground motion levels for each spectral parameter associated with a given probability, for example, 10% probability of exceeding in a given period of time, for example, 50 years for a selected size. In the end, all of this information, together with their uncertainties in size, space, and time, are introduced into the seismic hazard calculations. The most recent PSHA models involve different assumptions and approaches based on various seismological, geological, geophysical, geodetical data to reduce especially the epistemic uncertainties through the logic tree. Most of these models use the smoothed seismicity approaches for background seismicity, or when available, they adapt fault-based models and the time-dependent renewal models. In my presentation, I will show you some examples of the earthquake rate models constructed using different approaches, assumptions, and different databases, and their impact on probabilistic seismic hazard maps. I would like to start with the smoothed seismicity-based models developed following the smoothed seismicity methods that apply, these methods simply apply a Gaussian filter to smooth the earthquake locations from catalogs. And they assume that the location of small earthquakes forecast the spatial distributions of future large and potentially damaging earthquakes. In this slide, I showed you two earthquake seismicity rate maps for earthquakes magnitude larger than 4.5, constructed using Italian seismicity catalogs, adapting two different smoothing approaches. The first model is established following Frankel's 1995 well-known approach that applies a single smoothing distance for all earthquakes, while the second one, the adapted smoothed seismicity, defines unique smoothing distance for each earthquake. Although the total seismicity rates are pretty similar for the two models, they present significant variations in the spatial distribution, especially where the density of seismicity is very high and very low. This variation has an important impact on the final seismic hazard maps. The differences, for example, in this case, reaches up to around 0.1 G when we compare these two maps. Another assumption followed in the standard PSHA, as I mentioned previously, is the Poisson process. So to hold this assumption in the seismicity, we generally decluster the catalogs. So in the upper three panels, you can see the distribution of seismicity in the central Apennines. For earthquake larger than magnitude 3, as the one being from the complete catalog and the two from the declustered catalog. So catalogs are declustered following two widely used Garner and Nopov 1974 and Reisenberg 1985 algorithms. At the bottom panel to the right, we observed that Gardner and Nopov removes more earthquakes than the Rosenberg algorithm. This directly impacts the B-value, as observed at the bottom panel to the left, where the B-value is biased and small for the low magnitude of completeness. However, the B-value estimates present similar results for each catalog for events larger than 4.5. This slide shows the PGA maps are calculated using the instrumental seismic catalog declustered with Gardner and Nopov and the Rosenberg algorithms. Maps for PGA show a high acceleration around 0.5 G from the Rosenberg declustered catalog, while the ground motions are lower around 0.3 G for the Gardner and Nopov catalog, because the later approach removes many more events and results in a lower seismic hazard. However, in this slide, I would like to show you the impact of including the foreshocks and aftershocks on the probabilistic seismic hazard analysis. In the Taroni-Akıncı 2021 Geophysical Journal International paper, he proposed a new approach that allows for counting all events in the complete catalog, in complete seismic catalog, by simply changing the magnitude frequency distribution as a correction on the B-value and annual rate of events. The impact of the clustering on the seismic hazard analysis is illustrated in this slide with two maps, as the differences in PGA value with the corrected seismicity rates and the seismicity rates from two declustered catalogs. Here we observe that the hazard, calculated from the declustered catalogs was always lower than the hazard computed using the complete catalog. In general, the seismic hazard calculated using complete catalog leads to increased exceedance of ground acceleration in PGA around 0.1 G at probability levels of 10% in 50 years. In the lower corner panel, we present the seismic hazard curves calculated for the city of Norcia. Seismic hazard is larger for the model derived from the Rosenberg declustered catalog, because the algorithm removes a small number of events from the complete catalog, so resulting in higher seismicity activity compared to that obtained from the Gardner and Nopov 1974 for catalog. Okay, so another model commonly used in the seismic hazard analysis to calculate the seismicity rates for large earthquakes is based on the fault and geological data. If we have sufficient information about faults or fault systems responsible for large earthquakes, the annual occurrence rate for each structure can be calculated using the parameters, fault parameters such as slip rate, fault length, fault width, depth, and so on, assuming that the total seismic moment for a fault source releases with a single maximum magnitude event. So in the following few slides, I would like to show you the impact of different earthquake models based on different databases used for characterizing both spatial and temporal distribution of earthquake recurrences on the long-term seismic hazard. I will give you an example again from the Central Apennines, where we have complete knowledge about the recurrence rates for most of the seismic sources. For most seismic sources. In this region, we developed two models based on both seismicity and the geological information. In the seismicity-based model, we used the historical earthquake catalog and fixed smoothed seismicity model for earthquakes magnitude larger than 4.5. In the fault-based models, we consider only faults as an extended source for events magnitude larger than 5.9. These are the maps presented in PGA with 10% exceedance probability in 50 years. The map on the upper panel is calculated taking into account only the individual sources and active faults associated with strong earthquakes. However, the map on the lower panel is calculated using distribution of historical seismicity. As can be seen clearly, the spatial distribution of ground motion is quite different in the two maps. The seismicity-based model indicates zones that can be the location of future events, while the fault-based model indicates areas where, with high ground motion, very detailed, presented in a detail. This is the map created by integrating two models using a magnitude threshold being 5.9, so that the final map involves and considers various information and database and present a complete description of seismic hazard in the region. The figure shows the probability of two events associated with two faults in the Central Apennines in the next 30 years. It's calculated using the probability distribution function Brownian passage time, which is time dependent, and the Poisson model with time independent behavior. The horizontal lines present the Poisson probability being constant over the time. However, the Brownian passage time probability increases with time right after the earthquake. The vertical lines indicate the actual time is given by the elapsed time ratio that considers the time passed from the last event. If you can see on the Ovindeli-Petso fault, the last earthquake had occurred 774 years ago, and its recurrence time is 707 years. This means that it's close to its cycle and has larger probability of occurrence concerning Poisson probability. The hazard is not sensitive to the elapsed time in the Poisson model, and this information is not required. However, the renewal models require additional parameters, such as the elapsed time since the most recent event and the periodicity of each fault. This slide presents two maps calculated following the Poisson to the left and the Brownian passage time as the time-dependent hazard map to the left. In the time-dependent hazard map, as you can observe, the PGA value increases in the southern sector, where the probability of occurrence exceeds that of Poisson, especially in structures with a long lapse time regarding their recurrence time. For these sites, the time-dependent PGA value is around 0.5 G, while it's 0.3 G in the case of Poisson or time-independent model. The ground motion parameters are another crucial ingredient and one of the most important components of PSHA. They usually describe the observed attenuation of the ground shaking with distance and the amplitude scaling with magnitude. They are mainly derived from the strong motion data and are given by this kind of polynomial equation. Unfortunately, the presentation of the ground motion through the GMPs is a substantial simplification compared to complexity of physical progress involved during an earthquake. The uncertainties related to the source rupture and seismic wave propagation between source and site are associated with only a sigma parameter in the equation. Moreover, they have important limits to be developed regarding the availability of data, particularly for strong earthquakes in the near-field area. They have relatively simple mathematical form that depends on the relatively small number of independent variables and equation coefficients. For example, most of the ground motion predictive equations do not provide predictions that counts for near-fault effects, such as rupture directivity. This effect is very often observed in the recorded data from moderate to large events. During one of the European projects, MARSITE project, we attempted to include the directivity effect to PSHA for Istanbul. We used an analytical model for directivity proposed by Spudic and Chu 2008. This model provides the corrective coefficient, additive term, let's say, to some of the NGAs. This figure shows the peak spectral acceleration map for a period of 3 seconds, derived from the standard PSHA formulation, let's say, using Burr and Atkinson 2008 GMPs on the central Marmara Fault. Where we don't observe any directivity effect on the ground motion. However, these two figures shows a relative contribution to the corrective factors. We observe that the isolines are elongated in the strike direction, following the fault geometry and the position of the earthquake nucleation point. Finally, we observed that the effect of rupture directivity is to increase the seismic hazard estimates up to 25% at 3 seconds. Here I present the hazard curves calculated for the city of Istanbul, using two scenarios as being the worst case and the most probable one. The most probable density function for hypocentral location over the fault is obtained from the numerical simulations of the dynamic rupture generated by Auchi and Ulrich 2015. Because this information is not available a priori and is challenging. As you can see on the hazard curves presented as a function of period in both cases, the long period ground motion hazard is larger for the modified PSHA hazard curves that incorporate the rupture directivity effect concerning those resulting from the standard practice. The increased hazard in the longer period is an essential parameter for the critical infrastructures, especially for the high-rise building doing the part of Istanbul. To overcome the lack of information and data in the near field and reduce uncertainties associated with the ground motion models, the Southern California Earthquake Center, SCEC, has developed CyberShake. It's a simulation platform that performs physics-based probabilistic seismic hazard analysis using 3D deterministic wave propagation simulations. The CyberShake uses the propagation simulations of the entire 3D waveform calculated through powerful computational tools, supercomputers, to predict ground motions. The simulations are generated from many types of specific ruptures for many sites, such as virtual stations, for future moderate to strong earthquakes. It seems that these physics-based earthquake simulations probably account for source directivity, Bayesian effects, directivity Bayesian coupling, and other 3D complexity. In fact, the preliminary results shows that simulations can potentially reduce sigma by about 1/3 and could lower the exceedance probabilities for high hazard levels by order of magnitude. Of course, this would have a broad impact on risk reduction strategies, especially for critical structures. I'd like to show you last few slides, a couple of slides, on our effect shown towards generating 3D deterministic ground motion simulations for the magnitude 7.5 October 30, 2016 North earthquake. This earthquake is recorded by many digital stations and contains large number of registration in the near fault area. In this study, we aim to test end-to-end modeling capability for strong motion simulations and validated those against recorded data to be able to predict realistic ground motion. To calculate our simulations, we constructed 3D velocity crystal model using some thermographic studies carried out in this study area, a kinematic rupture model adapted from the previous studies. The simulations were performed by running the parallelized CPU version of the SW4 computer code on the supercomputer Quartz at the Lawrence Livermore National Laboratory. So the detail of this information you can find in Pitarka et al. 2021 BSSA paper, which is published a month ago. Here are the very interesting main results obtained in this study. In this slide, I present the spatial variations of simulated PGV values over almost 9,000 virtual stations close to the fault rupture. We observed that the large ground motions were obtained along the ruptured fault plane and the high mountain, local mountain peaks. We noticed that the ground motion amplification pattern depends very much on the relative location of the large slip patches. And the strongest ground motion are observed over the faults plane hanging fault sector. The largest PGVs reaches approximately 150 meters per second, where the damage observed damage was also high. So these results suggest that both the 3D surface topography and large slip areas are the key modeling parameters in seismic hazard assessment in the study region. And this is not well defined in the ground motion predictive equations, of course. Okay, I think I should stop here and come up with some conclusions since I have limited time. Here are my conclusions. I may say that to improve standards in PSHA, we should use multiple data and geological, geodetical, seismological data. We try to use time-dependent models for a more dynamic PSHA map, although it can be applicable in a few areas because we know little about some parameters for the majority of seismic sources. We should consider more physical parameters for ground motion estimation. We can use physics-based simulations. Of course, at the end, always we should carry out analysis on the uncertainties from different parameters in the calculation of hazard and quantify their impact on the produced results. Okay, I thank you very much for your attention. I hope you enjoy my talk and everything was clear. In case you have questions, I will be happy to answer.
Okay, I think Aybige Hocam is just live on the other side of the Zoom. Can you just let her appear on the side, please? Thank you very much for the presentation. Can you hear me? Aybige Hocam.
Evet duyuyorum. Siz beni duyuyor musunuz?
Hocam gayet net duyuyoruz. Güzel bir sunumdu. Çok teşekkür ederiz. Bizim için oldukça güzel şeyler aktardınız. Yani keynote lecture'larda arzu ettiğimiz tam seviyede çok güzel bir konuyu aktarmış oldunuz. Bunun için ellerinize sağlık efendim.
Soruları beklerken nazik davetinizde böyle önemli bir toplantının düzenlenmesinde emeği geçen herkese kendi dilimde teşekkürlerimi sunmak istiyorum. Tekrar çok teşekkürler. I couldn't help not speaking a few words in Turkish. Of course, it was just a short Turkish gratitude message to my colleagues for their kind invitation while we were waiting for questions. And thank you very much again for inviting me as a keynote speaker to this meeting. It is very well organized and successful meeting, and it is a great pleasure to me to join you here, even in a virtual platform. I wish I would be there in person, and hope this would happen soon. Yeah, thank you.
Okay, so hopefully in the following days, months, we are going to see each other physically. Okay, do we have any question from the audience? Is there anybody here who would like to ask a question? We can just circulate the microphone. Yeah, we have one question.
Thank you, Professor. Barış Ünal, Middle East Technical University. Actually, I have two questions about ground motion simulations. The first one is, how do you approach frequencies higher than 5 Hz? You mentioned your simulations are for the 0 and 5 Hz range. And I can ask the second question, if I may. Second question is, how do you approach the validation of the simulation results in a region where the real data is not very available? Thank you.
Yeah, thank you very much for the questions. and for your interest to this research, and how we get this higher acceleration or frequencies. It's you use stochastic approaches and small-scale stochastic statistic approaches to add this variability. And in our latest paper, we explain it in a good way. I believe I can send it to you. It's a technical approach that I cannot really explain clearly here. How we test these results. In fact, as I said, in Norcha area, we did it because we had a plenty of recordings in the near fault area. So this permitted us to compare our simulations with the recordings as well. For example, for areas that we get the largest accelerations or velocities, unfortunately, we didn't have recordings. The simulations are generated over 9,000 virtual sites where we don't have recordings for this number of simulations, unfortunately. But when you have this kind of information, you can test your results. There are earthquakes registered in the near source that permits you to make this kind of process.
Okay, thank you. May I add one more question to this, if there are no questions? Yeah, so if it's possible to validate our simulations with the ground motion prediction equations, where, for example, we can we validate them for example, not so large earthquakes and not so small distances, and then after validating, can we use these simulations for near fault effects or near field estimations?
Yeah, the problem is to get more information in the near fault, because where we get the most damage, right? The problem is this. To overcome this problem, we start generating simulations. Because we don't have enough data from larger earthquakes, for large earthquakes. And for intermediate distances and longer distances, of course you can use ground motion predictive equations, at least to see where you are. But as a seismologist, I can say we are interested in mostly to understand the physics of the earth. So to understand how the wave propagates through the earth, because in different regions, you have the different attenuation behavior, right? In the active zones, we have different GMPs. That is why we have different GMBs, and the continental crust, where the crust geologically completely different, you have the different attenuation coefficients. But yeah, sure, we can use GMPs to test some distance range, that if you are doing okay or not. But this kind of research beyond this, beyond to understand the physical process during an earthquake. Okay, it's not a simple comparison with a curve, because Earth is much more complex than that.
Thank you very much.
Is there another question from the audience? I think we don't have any more questions indeed. Okay, Aybegü Hocam, çok teşekkür ederim. Thank you very much for the presentation.
Thank you very much.
Okay, so we are going to go to the next keynote lecture. Okay, we have minutes, I think. I think we can just go to next. We can pass the next keynote lecture. And again, the second keynote lecturer, the next keynote lecturer, again from Italy. And then his Professor Fabrizio Mallioli from Sapienza University, Rome. And then let me check whether he is connected now. Dün dediğim gibi yani...
Yes, I'm connected.
All right, so Fabrizio is here. Then...
I'm going to...
Okay, I see now.
Okay.
Okay, we can see you. All the audience can see you here. Thank you. Okay, good day. It is 11:30 in Rome.
It's 11:30. Exactly.
It's just midday in Istanbul, in Gebze, and then we are going to have you. Okay, let me just introduce you, Professor Mallioli. He attended his degrees in the 90s in Sapienza University, and he's been a full professor in the Sapienza University, Rome. And then he's going to give a very interesting lecture. He's going to give a very interesting topic indeed. And that topic is supposed to be the future of the structural engineering. And I'm sure you're going to have fun and you're going to enjoy his talk. Your turn.
Yes, I'm trying to go on. Please, you must habilitate my condivision. Hamet. Yes, but the condivision is not habilitated. Okay, okay. Well, now it's possible. Okay, can you see my presentation now? Perhaps I needed to connect everything, perhaps. Let me see. Now you can see? Perfect. Sorry for the delay. Firstly, I would like to thank you and the president, the organizing committee for this kind of invitation. And my presentation will try to make some explanation about the fundamental topics of the energy approach in seismic engineering. And I would like to start with some philosophy in order to explain that energy balance or the conservation of energy is a very common law in nature, and for a physician is very familiar, and also for us it is easy to apply, just like equilibrium. Moreover, the energy balance include the main parameters that we have used until now for the design of new and the assessment of existing buildings. In other words, force and displacement, because it includes both of these aspects. It started a lot of years ago in 1956 with George Hausner, more or less, and here that I only show you the first lines he produced in that period, but we have to wait until 1988, more or less, with the very famous book of Professor Akiyama, Earthquake Resistant Design Based on the Energy Concept. And on the right side of the screen, you can see the version adapted from Professor Benavent Climent of Spain in order to explain the main aspect of this topic. In this book, more or less everything about the energy-based design is explained and at the time with 3 or 4 rigors, not so much. But the main aspects are well explained and well described. In Japan, they went on with the application also with the energy-based design, but in the rest of the world, there was we had to wait until the Vision 2000 document for the performance-based seismic engineering of buildings, and mainly due to the work of Professor Bertero, that started before in dealing with the energy-based design. And also he underlined during an interview very important things. Is an energy-based seismic method useful for application by practicing engineering? At the time, he explained that yes, but with time. We needed to prepare future codes taking into account energy-based design, but gradually in order to be adopted in practice. But now we have more information about this application. Here are the 2 famous balance equations for the relative and the absolute input energy. But the most important aspects that were already studied in the past is that generally in energy-based design, both input energy, absolute or relative, is not important. This aspect depends exclusively to the total mass, the fundamental P of the structure, and no matter with viscous damping and the inertification and the number of degrees of freedom. Moreover, another important aspect, force and displacement are vectors. In fact, we make a lot of works in understanding what is the critical direction for the seismic response. Energy is independent of choice of directions. Then, energy demand include more damage-related information that, of course, peak displacement or acceleration. Acceleration is PGA in particular is considered the worst parameters in describing the damage to the structures. Energy takes into account simultaneously amplitude, frequency content, and duration. That are the main parameters useful for the design. Here only to show you that the difference between the absolute or relative input energy is not so important. At the time, Professor Bertero underlined that between 0.3 seconds to 5 seconds, they are almost equal. In fact, they change in the high frequency and the low frequency region. There are some cases where this difference are higher, but from a statistical point of view, the difference is not so particularly high. But I would like to go inside, firstly, in an important aspect in the energy-based design that is one aspect that remain hidden for several years. Okay, the fact that the input energy depends almost exclusively on total mass and fundamental period correspond to an equal input energy rule that plays a central role in energy-based design. The equal input energy rule is completely different from the equal energy rule used by Veletzos and Newmark, and also adopted in more or less all the worldwide codes. In particular, if you look at this equation, I don't want to bore you with algebra manipulation of the equation. I show only the final result. On the left side, you can see the equation suggested years ago by Akiyama for the equal energy-based rule, and this is the equation of Velezos and Newmark. There is a key difference between the two equations. The former use the cumulative hysteretic energy dissipated by the system during cyclic reversals imposed by the earthquake, while the latter is obtained equating the area below the force displacement curve up to the maximum displacement. These are represented the energy that is stored and dissipated by the system under monotonic loading up to the maximum displacement. Velezos and Newmark adopted this energy as an aid to phenomenally related elastic and dynastic responses of the system. They did not attempt to evaluate the energy input by the earthquake on structures. This misunderstanding hindered the development of energy-based design until now. Here there are some parameters. The ratio between the plastic displacement and the elastic displacement, according to the Akiyama after algebra manipulation of the energy balance equation. These are the two equations possible derived from a Newmark approach. If you look at these pictures, it's possible to see that in terms of displacement or in terms of resistance defined by this other ratio, you can see the difference between the two Newmark approaches and the other, derived from the Akiyama equation for different number equivalent cycles. More detail can be found in the publication highlighted below. Another aspect that we discussed is that input energy is scarcely affected by viscous damping ratio. There are a lot of authors that discussed about it. In particular, started a lot of years ago with Professor Pfeiffer. Also, my work at the beginning in the 90s was devoted to this aspect, and many others show this. You can see in this picture the difference between the different damping ratios on input energy, in this case, equivalent velocity. This does not mean that damping have no influence on input energy. The question is that the influence is small in comparison with the variability due to the damping. On this topic of damping energy, there are also recent studies. Professor Fardis, during the last European Conference on Engineering, highlighted some aspects that should be better clarified in the damping energy, and also recent paper, Professor Sujolu, on this topic highlighted other important aspects. Anyway, after this premise, the purpose of my research, and not only mine, is devoted to address the following issues. Are the energy-based intensive measures able to characterize the damage potential of ground motions? Do we need to look for energy-based engineering demand parameters? How to evaluate accurately the capacity of structural members in terms of energy? How can damage be estimated in terms of energy? What is the influence of structural modeling in energy-based damage assessments of structures? How can the energy dissipation demand of structural components be estimated from the total input energy? There are also other issues very important, but I would like to put attention in some of them. Firstly, when you are talking about intensity measure, in other words, in performance-based design, we are looking to the first part, how to connect the hazard analysis in terms of energy with good parameters that can describe the response of the structures. But I would like to underline two aspects. We are two ways taking into account from a physical point of view and from a statistical point of view. Because often in performance-based design, we are more concentrated to the statistical point of view. But an important aspect is if the physical point of view. From this point, it's possible, according to my opinion, the fact that the energy takes into account frequency content, duration, and amplitude of the ground motion is a very important aspect. Let's see. I would like to start with an example shown by Professor Bertera a lot of years ago. Here I only re-elaborated some of these aspects. There are two earthquakes, in particular two recordings in two earthquakes. The Chile earthquake, Yoyeo record, 1985, magnitude 7.8, at 33 kilometers from the source. And the San Salvador earthquake of 86, sorry, magnitude 5.4. If you can see also, there is a pulse present in the San Salvador record, while it is not present in the other record of Yoyeo. If you will look at the spectral acceleration of the energy spectral response, we can see that the acceleration for the two records is more or less always the same. Big difference there is between the two. Moreover, there are some peaks in the Yoyeo record that is characterized by the fact that there are a lot of a larger frequency content in velocity and acceleration in this record. There is only one peak practically in the San Salvador. In this case, they correspond exactly, the period of this maximum peak corresponding exactly to the duration of the pulse. Or let's look to the classical parameters used. Arias intensity. Arias intensity is the square integral, the integral of the square acceleration. And here is with the blue line. Okay, we can see this is a particular record that has a late pulse in this part. Okay, we can see this increase in two parts, in the high frequency part and the low frequency part. While the energy has a big increase, in this case, the energy flux only is the squaring. To simplify this analysis is the integral of the square velocity. And correspond this increase in the energy part to the maximum displacement demand and the maximum velocity demand. This aspect, as I already underlined, is possible to see that the pulse corresponding to, here is the pulse in acceleration, but it's in velocity and displacement. The period of the maximum corresponding to the duration of the pulse correspond exactly to the duration, to the peak energy demand period. There are a lot of examples dealing with this. Here, as you can see, this is a Taiwan records full of high frequencies, but there is a part that in the velocity is possible to highlight that there is the presence of a pulse. Also in this case, the Arias intensity increase because depends only on the acceleration, increase continuously with no particular differences. While the energy increase in the part corresponding to this pulse, but corresponding also to the maximum displacement demand. The correlation also between energy and displacement can be highlighted here for the different different records. Sorry, Helsinki record, pulse-like record, Hachinohe record, very long duration record. These are normalized to the maximum values, and in particular, the I performed this analysis to a large number of frames of different period, and it's possible to see that the drift demand, maximum demand, corresponding exactly to the same shape of the energy demand. Spectral acceleration is apart from this for both the records. There are a lot of examples in order to understand what does it means, the importance to take into account simultaneously the influence of amplitude, frequency content, and duration, not singularly by different other parameters. In order to demonstrate also this, we performed, here are some publication about this, from a statistical point of view, the goodness of the intense energy-based parameters. In this case, okay, we analyzed bare frames with base isolation, with dissipative braces, and so on. We studied efficiency, sufficiency, practicality, algebra compatibility, as is normal to consider when you are making this kind of analysis. We consider a lot of intensity measure, and in particular, some intensity measure based on energy. We have seen that the energy-based intensity measure are very efficient predictor, not only for the information response of the classical frames, but for the isolation system, for the moment-sensitive frames, frames with dissipative devices. In other words, while, for example, for some frames, the spectral acceleration at T1 can be an efficient of about 92–93%, while the energy is at 90%, so it's less efficient than SCT1. In general, for all this kind of structure, the energy-based intensity measure are very efficient predictor. Therefore, in order to apply this information energy-based design methodologies, we need a framework of these energy-based design methodologies. Here are some various proposals during the past in this field. I'm saying we because this involves also the work we are having together with Professor Benevan Clement on this topic. Prefer to extend the Akiyama methodology because it is really based on energy, only on energy. The other parameters, force and displacement, are derived from energy directly. Okay, therefore, we perform prediction equation of input energy or equivalent input energy. Once they are known, of course, it's possible to define other, just like Hausner intensity in terms of energy or other intensity measures. Once this is known, the evaluation of the static energy, this is the part very important in order to understand in which way we can dissipate energy in a structure, is derived from the ratio between static energy and input energy, that is function, damping, static model, ductility, or strength demand. Once the energy dissipation demand, we have make this characterization. In this paper, we highlighting below, we perform this kind of prediction equation also for other two parameters that I'll describe later. Well, when the static energy demand is known, it's also necessary to estimate how to distribute the static energy along the height of the building at the local levels for the story, for the members, and so on. Here, this is the general methodology. Of course, this is a synthetic way to look at this methodology. There are, first for the demand, we start from the balance equation. The demand, for example, in equivalent velocity, is based on the parameter that I explained before. In order to supply, we usually Akiyama divide it into two parts: the elastic energy for structure not involved in significantly elastic excursions, and the supply. Okay, in order to define the hysteretic energy that needed to be supplied by the structures, it's necessary to introduce two other parameters: the number of equivalent cycles and the parameter eta, that is defined by the ratio between hysteretic energy and the product between yielding and displacement, yielding force and displacements product. The cumulative hysteretic ratio of generally a single degree of freedom system, usually related with the cyclic behavior, is defined by this parameter eta. The equivalent number of cycles relate the strength and the maximum apparent inelastic displacement of the system with the hysteretic energy demand of earthquake. Both parameters can be used for the design standpoint to obtain the required lateral strength, this parameter Qy, for which the structure is capable of dissipating the hysteretic input energy without exceeding a certain ductility level. It's better defined by this two equation in order to obtain this value, as it's possible to see number equivalent cycle is related to the parameter eta and me. This is for single degree of freedom systems, while on the right there is for multi-degree of freedom systems. After some also other algebra manipulation, it's possible to show this equation. The ratio between the dissipated energy, the number of equivalent cycles, is equal to this product between force at the yielding and maximum displacement, at which can be subtracted the ratio between the squared yielding force with divided by the stiffness. Representing in graph this equation, this is a parabola, okay, where it's possible to define for different level of hysteretic energy, different forces necessary to obtain a predefined displacement. Therefore, the design disposes of several values of Qy that lead to dissipate hysteretic energy achieving the maximum displacement. Anyway, in order to distribute this kind of hysteretic energy along the height of the building, there are several approaches. In this part, I show you two papers in which I define the new optimum distribution of lateral strengths for classical shear type buildings, and while Professor Benjamin Kliman and Donaire Avila define the optimum strength distribution with metallic dampers. These are the equations necessary to define this. We start from the classical balance equation, the hysteretic energy at the constant ductility, for example, but also we can make this as a constant strength, is defined in this way. But as suggested by Akiyama, it's necessary to define alpha I is the optimum. Sorry, it's not the optimum. The strength demand at each story. Okay. Why alpha 1 is the strength demand at the base, and alpha I is the optimal one. The optimal one is defined in a way that the system is capable of absorb and dissipate the hysteretic energy demand under an even distribution of damage. In other words, assuring that the parameter eta at each story is equal of the general parameter eta In other words, it's constant. Then, after some other simple algebra manipulation, it's possible to define the part of static energy that corresponds to each story. Here are what happened. The main problem is that it's very sensible, this distribution, the optimal distribution, to the kind of records. So, particularly for higher stories, described in the last graph. But we have defined this optimized distribution for this kind of parameter. Anyway, this is the general methodology of the time at my disposal permit only to describe the main aspect, not to define all the aspects. Now I would like to try to define a very big problem, how to evaluate accurately the capacity of structure members and systems in terms of energy. It's one of the questions that I posed at the beginning of this presentation. For non-deteriorating structural components, it's like steel. It was possible already. Benevent Clement defined how to do it in decomposing the two parts, Bauschinger part from the skeleton part. Here are the skeleton part and the Bauschinger part. The two parameters are there, and correlate it with the damage expressed in from experimental test. This comparison was quite good. The problem that we are facing now is to define this kind of definition of capacity in terms of energy, also for deteriorating structures like reinforced concrete or masonry. This work is under development until now. But also, another question that should be answered in the future is how can the damage be estimated in terms of energy? We have to define, in order to complete the part necessary to define a full performance-based design, we had to also define collapse limit states and other limit states. In which way? With damage indexes? It's not clear until now what is possible to do. Here for the collapse, there are some criteria adopted very recently, but also I work in another possibility to define only the collapse for a normal structure. And in this research, we have found that once the collapse begins, the kinetic energy in the external work increases significantly, immediately. It's possible to evaluate this sudden increase of kinetic energy. Therefore, for us, the definition of this collapse limit state is based on the difference between the kinetic energy during the motion, because at the end of motion, the kinetic is 0, and the input energy. In other words, when this is a part of the motion, during the motion for a single degree of freedom system, in this case, when the kinetic energy, the red one, touch the input energy in this way with a sudden increase, for us, this is the time at which the structure collapses. And we have information in this time about also the hysteretic energy that produce this. We have checked this in equation, this equation with a single degree of freedom system and multi-degree of freedom for steel at the moment, also based on experimental test. The advantage of this is that with respect to other suggestions, there is not necessary to scale the records to very large number, as is useful to do for other indexes in this field. This is my conviction. According to me, to scale the record to very large number correspond to modify without no connection or in magnitude, distance, and cell condition of the record. But also the other possibility is to work with damage indexes. But well, the damage index usually in the past, is particularly the Parker-Hannington damage index, is a compound indexes. In other words, takes into account at the same time the contribution of displacement and energy and forces. In this case, we can overlap the 2 times, for example, the contribution of energy, because we are taking into account displacement and force again. Bogsoni and Bertero in 2001 modified this index in order to avoid this problem with the Parker damage index, but also there are other indexes. I would like to stress the fact that perhaps it's better to work directly on energy. Here there are some indexes that could take into account the cumulative behavior. In other words, takes into account only the energy, the sign, and the energy parameters. I'm going to the conclusions, but would like to talk about some needs, potential, and prospects for the energy-based design. Some of them I have already discussed, particularly the capacities of various types of elements to dissipate energy is very important to define as a function of geometry and material properties based on experimental tests. Energy-based procedures should be devised and applied on the basis with the goal to reduce or accommodate energy demand. Development of an improved and comprehensive energy-based approach for seismic analysis and design of ordinary structures, with the establishment of a common understanding of energy-based seismic engineering. In other words, everyone would like to develop a new methodology, but discussion between groups, between researchers, is important to establish a common understanding in this field. Then the final should be, of course, to transfer all the information in a probabilistic framework to attain the goals of the performance-based earthquake engineering. Future direction. To develop all the aspects that they were discussed until now is important to fostering knowledge and data exchange on energy-based assessment between the researchers. Promotion of the energy-based approach in the next generation of European building code, of course, is a longer period activity to the development of particular or specific guidelines to be applied in code of practice. Strengthening the international cooperation about the new concept of the seismic analysis and design of structure, and development of a joint research and teaching agenda about energy-based seismic engineering. In my recent research activity, I try to push with the collaboration of a lot of other colleagues. Also, Professor Dindar, that is the president of this session, participated to all this activity. Here, there are the last production. We have made the first international workshop on energy-based seismic engineering in Madrid, unfortunately, not personally because due to COVID, the pandemic. And we produce this volume. And also we plan to have the next workshop in 2023. The location will be decided. Also, within Energy Frontiers in Built Environment, we organize an energy-based seismic engineering research topic. I would like to invite everyone who wants to publish there. The submissions are open. Until December, it's possible also to submit an abstract and then the paper. And we trying to produce to work to obtain the fund of the cost action until now with no success. But we were also planning a new one that will be led by Professor Amadea Benavent-Clement, perhaps at the end in November, but more probably the first one of the next year. Everyone who is interested, please let's inform us. The last one was involving a lot of countries. In this picture, we have a picture of also the European countries involved in this, and also in this list, the other extra European participants. And final, we have also organized a website in order to diffuse this activity. Anyone if you want to be part of it, please, it's very easy to join us. Perhaps we will migrate to another platform, but the problem is it's not for you, it's not only for us. And this is the site. And everyone who wanted to participate to this is welcome. Thank you for your attention.
Fabrizio, thank you very much for the presentation, because this topic is a very interesting topic, and then we believe this is just going to be the future of the next generation seismic codes and next generation seismic engineering indeed. Fabrizio, can you hear me?
Yes, yes, I can hear.
All right, so if we have any question from the audience, we can just ask to Fabrizio right now. He has already provided very nice addresses, the website, and then the next year another workshop, and then probably we are going to be very active on that topic for the following years. But just for the moment, if you have any question from the, we have one question.
Buongiorno, Dr. Mollaioli, right? That's the exact pronunciation.
Yeah. Sometimes
yeah. Dr. Akbashir, Department of Civil Engineering, Gebze Technical University, and one of the authors in your reference list.
Thanks.
Thank you very much for this wonderful overview of energy-based design. And as you have pointed out, there are three important steps in energy-based design. The first one is to estimate precisely and accurately the energy input to the structure. The second one is we have to know how the energy is distributed or will be distributed throughout the structure in case of a strong ground motion. And the third one is to estimate the seismic energy dissipation capacity of the structural element so that we can come up with a whole structural design. And my question is, how far do you think we are away from accomplishing these three steps in energy-based design? You think energy-based design will be a practical tool for structure engineers in the near future, and seismic design codes will allow energy-based design in the specifications? Because currently, you know, whatever you do with energy, we convert it into lateral forces and carry out structure analysis, do all the design. But energy itself has the capacity of doing all the design stuff and coming up with the sizes of the structural elements. How do you think we are far away from this goal? Thank you.
Thank you for your very interesting question. We are not so close to obtain everything. Some of these parts are well described and well done. For example, the distribution of the hysteretic energy along the height of buildings is not a particular problem. It's quite easy to develop, and it needs only analysis, but a lot of them are done, other are ongoing. Then also, another question very important is the first part too, because to define, we have several prediction equations of energy. Here I presented myself, but also there are perhaps the first one was proposed by Professor Chapman in 1988, if I remember. No, 1998, sorry. And there are also Fournier fault prediction question proposed by Professor Suggiolo. There are also another question recently proposed by Binder and others. And also Professor Wang produced years ago another attenuation equation. But what is important to say on this topic, there is another question very important that to define, we discussed it during the workshop, to define the hazard also in terms of energy. This is particularly difficult because in modeling, perhaps from seismological point of view, perhaps could be an advantage if it is useful, because one thing is to work with acceleration and another one is to work with velocity. For seismologists, velocity is easier to consider. But the other question is, okay, let's define the hazard in terms of equivalent velocity or in terms of energy. This part is not very close. And the other part that is also far from the solution is what I underlined before, is the characterization of the capacity of in terms of energy. Is well done for the steel, but not already done for reinforced concrete and masonry, for example. This will take more time, but also the exchange of data between researchers. I believe, because we are also working with the actual next generation of European code, they are finishing in this period. This is not ready in this part, even though some energy-based design for dissipative device was proposed and included in the next generation of Euro codes. We had to wait more or less other 10 years for the other new generation of equivalent codes. Perhaps I will be retired. I hope that I answered to your question.
Any other question from the audience? I think we do not have any more questions. It seems we came to the lunch time. And then, okay, Fabrizio, thank you very much for the presentation. This is something pointing to the future, and we believe we are going to take place in that future together.
Thank you. Thank you for your attention. Thank you for the invitation.
Okay, so I end up the close for the lecture notes today, and this time, and then we go to the lunch. Thank you, Fabrizio. Bye-bye.
Bye-bye.
Pardon hocam, bir duyuru yapacağım da saat 6.30'da deskin önünde toplanıp saat 7'de gala yemeğine geçeceğiz başka bir restoranda. Eğer gala yemeğine geçmek isteyen varsa lütfen deske bildirebilir mi? Bunu sayı almaya çalışıyoruz da. Teşekkürler.